Okay, we have a few problems. You can see this, f of x equals negative x squared, g of x equals 2 to the x. What are f of g of x, g of f of x? What are the domains and ranges of f circle g and g circle f? I'm going to do these, and some of you, I think most of you, in fact, didn't get this assignment done. Okay. So you're going to have to go to the link work page, which is ordinarily half credit. Okay. Through our next class, I give you full credit. So this is going to help you make more sense out of the assignment when you do it. Okay. Busy week. It's easy to get behind, but remember, you want to stay on top of it for the credit, as well as for the fact that you learn more in class if you're well prepared. Okay. Not being critical. I know how life can be. Once in a while that happens. And most of you have been very, very good about staying on top of things. Okay. So matter of fact, everybody here has been very good about that. One thing you got to understand is if you go into the main course and do the assignment after it's due, it'll keep the assignment open for practice, but it's practice. When you go to submit it, it ain't going to submit. Okay. So it's there for practice. If you go to the half credit page, the late assignment page, did you get an email on that? I'm pretty sure I did. I had one student from another class email me. I sent those out at the same time, essentially. So I'm pretty sure we did. But anyhow, use that link and go to that page. Okay. No, I digress and forgot what I was going to say. But another thing I need to say, and I think this might have been it, is after you've done an assignment, now when you do an assignment, typically you've got a lot of help from the videos. I don't have videos on every problem, but on most of the early ones, there are videos. And there are videos in the majority of problems. Okay. If you're doing the problems by imitating the videos, maybe you're not really mastering it. So what I recommend is you take 20, 30 minutes. It's hard to even find 20 or 30 minutes. It is for me too, but you find 20 or 30 minutes, even 10 or 15 minutes, and go back and look at the problems that you did and think about how they're done. That reinforces what you learned, even if you were doing the thing by imitation in the first place. Okay. Remember, your goal is to prepare yourself for these daily quizzes. So you need to incorporate as much of the information as possible. Okay. And then again, it makes it much easier in this course and your pre-calculus course. Okay. With those comments, we're going to move on. Remember, okay, f of g of x. Well, first of all, let's write out f of x equals negative x squared. Okay. And g of x equals 2 to the x. So that I'll write it out. F circle g of x is f of g of x. We use the f circle g so we can talk about the f circle g function. This is how we work it out. Okay. So it's f of g of x. Well, f of g of x is what? Well, what have we substituted for x? We substituted g of x, right? Then we don't have to worry about what that means or anything. But if x is replaced by g of x, we'll replace x here by g of x, which gives us negative g of x squared. Okay. And of course, g of x is 2 to the x. So one more step and we have it. We have a negative of 2 to the x quantity squared. Now, I'm not sure that the assignment I gave you on exponents did the rule for a power of a power, but we talked about this. Okay. And of course, what this means is a negative of 2 to the x times 2 to the x and 2 to the x times 2 to the x, using a rule that you do know from your assignment, is 2 to the 2x. 2 to the x plus x. Let's write it that way. Just make sure that we're really split 2 to the x plus x. And now we can drop the parentheses because the rules of order of operations, okay? The order of operations tells you, you raise this, you raise 2 to the 2x, then you take the negative, okay? Okay, so that's your F circle G of x. What's its domain? Well, the domain is all possible values of x. There's no value of x that you can't raise to the 2x, or no value of x such that 2 to the 2x power isn't defined. So the domain is all real numbers. Let's see, have the domain. All real. Now, you know from your work on the basic functions that 2 to the x works just fine for positive x, it works just fine for negative x. And you get a graph that looks like this. And you should be familiar with that. And if you aren't, keep looking at it, okay? Because those functions, again, are the foundation of the whole course. What's the range? Well, you know that when you raise 2 to a power, it's always going to be positive. Okay? If it's a positive power, then you're going to get 2 raised to some positive power. If it's a negative power, you're going to get 1 over 2 raised to a positive power, and that's still positive. And you know from the graph that it's always positive. Okay? So you know that 2 to the 2x is always positive. Let's get a room here. The range going to write out the word positive. I'll say always greater than 0. Is that okay? You understand? Okay. So 2 to the 2x is always greater than 0 because 2x is just another power up that you're raising, another exponent of 2. And any exponent of 2 always gives you a positive number. And we can say that two to the x can be any positive number because, you know, if you go to the right, this thing gets really steep. There's no limit to how big it gets. And if you come over this way, it keeps cutting in half. It never reaches 0. But if you keep cutting something in half, no matter how close you want to be to 0, eventually you're going to get that close, right? So there's no positive number that isn't equal to 2 to the 2x, or 2 to the x, let's say, for some value of x. And the same is going to be true for 2 to the 2x, because 2 to the 2x is just another exponent. Now, that might be a little hard to grasp, but that's how we reason out the range. And when we get more familiar with the exponential function, we'll understand this even better. But from the graph you made, we should understand these statements. Go back and look at your graph, look at these statements. Make sure it works, make sure it fits. Okay. So say the range is the interval 0 infinity in notation. Doesn't include 0. Can't include infinity because infinity is not a number, it's just something you approach. This means any number all the way down to 0, but not 0, and any positive number, no matter how big. Okay. Okay, what? G circle F. Is what? Well, now, well, that's G of F. So we're replacing x by f of x in this expression. That's going to give us 2 raised to the f of x. And of course, f of x is negative x squared. That's 2 to the negative x squared. Okay. I actually alluded to this in class the other day. And I even said, well, this is a bell-shaped curve. Should be peaking at the y-axis. Should have drawn the curve before I drew the y-axis, but it is still missed it. But anyhow, you understand, you've seen this curve before. Okay. It's not the standard normal curve, but it's a vertical stretch. It's a standard normal curve. It's a little more complicated to reason out the domain and range. I'll just say it. Greatest this can be is, well, for any value of x, negative x squared is a positive number. Sorry, x squared is a positive number for any value of x. Because you square a positive, you get a positive. If you square a negative, you get a positive. So negative x squared is always a negative number, except when x equals 0. If you raise 2 to a negative power, you know from your calculations in the graph of the 2 to the x function, you're going to get a number less than 1. So 2 to the negative x squared is always less than 1 unless x equals 0, in which case you have 2 to the 0, which is 1. Now, I'm not going to go much further with the reasoning, but the domain is all real, meaning all real numbers, because there's no real number that you can't substitute into 2 to the x or 2 to a power. There's no power that you can't raise 2, 2. I was trying to avoid saying 2, 2. Okay. There's no power to which you cannot raise 2. So you put any number in here and you get a result. You're going to get a positive result. It's all positive because, of course, your exponential basic 2 to the x function always gives you positive results. We just talked about that. less than 1 if x isn't 0. It's equal to 1 if x equals 0. So the range is the interval 0, 1. It's worth thinking about. Worth taking another look at. Now, a simple example. Well, actually, okay. And we did simple examples last time. You can look at that. Okay, now we want to simplify. Some exponential expressions. Did pretty well in this. Let's make sure that everybody's on track. Okay. X squared y to the negative 3 raised to the negative 2. Now, if you write out all the steps, and I encourage you to do that to reinforce the rules. In the first place, you raise a product to a power, and you take that power of both of the factors, or all the factors, okay? So this rule, first rule, tells you that you get this. Then x squared to the negative 2 is x raised to the 2 times negative 2, and y to the negative 3 times negative 2. That gives you x to the negative 4, y to the 6. Okay, there are other ways you could write this out. Or meaning of the negative exponent, you do the reciprocal with the positive power. It gives you 1 over x to the 4th times y to the negative 6th. Well, x to the negative 4 is 1 over x to the 4th. And y to the negative 6th is 1 over y to the 6th. If you do the complex fraction, that is the same as y to the 6th. Okay. So that could be written as y to the 6th over x to the 4th. So there's some flexibility in how you simplify an expression of that nature. Now, ab squared times a cubed b cubed. We could write this as a times a cubed times b squared times b cubed. I encourage you to write it out this way. A times a cubed is a times a times a times a. B squared is b times b. B cubed is b times b times b. And then you just count your a's. You got a, you got 4 a's multiplied, that gives you a to the 4th. You got 5 b's, gives you b to the 5th. And if you think this through, it removes the temptation to multiply the 2 and the 3, which is real easy to do because you're in multiplication here. But if you multiply these, you don't multiply the exponents because that wouldn't work. And so the rule for exponents x to the y to the z is x to the y times z. X to the y times x to the z is x to the y plus z. I don't want to make sure you memorize these formulas, but you also want to make sure you understand why they work in terms of simple examples. See, don't confuse them because they're really easy to confuse. We worked on, we spent a lot of time last time explaining that. Okay, so you can always look back at the video, to that part of the video. All right. Now we have the last one. I'm not going to do that one just for in interest of time because there are other things we need to talk about. But I do want to address this graph. Just briefly. Got a graph of f of x and a graph of g of x. And this is my A number. In my case, that might be 5. Okay. And this is the D number, which I think maybe is 12. Let me make a table. Now, if we want to do a graph of f circle g of x, which is of course f of g of x. Well, if we know x, then the first thing we're going to do is we're going to find g of x. Okay, so let's just take a number here. Let's just take, this is 5. Let's say that 1 is about here. Then g of 1 is the y coordinate of the graph point corresponding to x equals 1. So here's g of 1. Okay. And that looks like, if this is 12, there's 6. Looks like it's about 6. Okay. So I'm going to say, we're going to estimate that g of 1 is 6. Okay, so for example, the word you can't read is estimate, just find estimate. That may look a little less like 6. Okay, find estimate. F of g of 1 equals f of 6. Okay, now I've got a little bit of a problem there because 5 is here, 6 is here. Maybe our graph doesn't go all the way out to 6. Well, I'm going to make it go all the way out to 6. So we can kind of extrapolate the graph. So here's 6. Here's g of 6. That's approximately, if that's 12, I'm going to say that's about 14. So my process is pick an x value, estimate g of x. In this case, x is 1, so we estimate g of 1 equals 6. And then do f of g of 1, which means you go to g of 1, which is 6, and take it up to the f of x function and estimate the value. So complete an estimate. If X is 1, if X is 6, and f of g of X is, we can write it out, f of g of 1 equals f of 6, which is approximately 14. Now, if X equals, let's just go 1, 2, 3, 4, 5, okay? If X is 2, and then 3, 4, 5. If X is 2, it looks like g of X is about, not quite 9, but I'm going to pretend it's I'm going to say it's 8.6. Okay. Well, that means I'd have to go out to 8.6 here. Means I'd have to extend my graph and make an estimate here. So unfortunately, I asked this in the wrong direction, but you understand, if you take a bunch of points here, you can find your f of X or your g of X's, and you can use those to estimate your f of X's like we did here. Instead of going out to 2, for example, we're going to go to 0. Okay, g of 0 is the coordinate here, and that is, maybe that's 10. G of X is maybe that's 8. Then that's still too big. Okay, well, that's the process. Again, I apologize. I kind of chose a bad example. But you saw that, or you will see that in your open math assignment. Okay. Graph, we got the 0.24. We want to shift the 0.24 1 unit to the right. What would the coordinates be? And where would that be on the graph? Okay, very good. People got that very quickly. I expected that you would, but I'd like to make sure, because if you don't understand this, you're not going to understand a word I say after this. Okay, you might not anyway, just going to come kind of garbled with these days for some reason. Anyhow, we have the 0.24. We shifted 1 unit to the right. Well, here's 24. We go 1 unit to the right. We end up at the point 3. And we're still at 4. So this is the point 3, 4. Okay, well, I'll give you a couple more points. As it should be familiar, this is the point 1, 1. And we have the point 1/2, 1/4. And the point 0, 0. Show me what you get if you shift each of these points 2 units to the right. 1 unit to the right, sorry. Okay, people did well with this, even though I would have needed a microscope to read some of your graphs. Bigger graphs are easier to label and they're easier to see. They're easier for you, which is even more important than making them easy for me. So I always know what I'm looking for, okay? And if I can kind of see it, then I kind of think you're okay. Now on a test, you really want to make it so it's legible. And if your graph is too small and I ask you to do a bunch of stuff in close to the origin and stuff, it gets real difficult. Okay, so just to highlight what I'm doing, I'm going to use some colors. You've got to understand this is pretty much what everybody did. Okay, so 1, 1 goes to 2, 1. 1/4, 1/2, 1/4 goes to 3/2, 1/4. And 0, 0 goes to 1, 0. Now, can you sketch a smooth curve through your original 4 points and then sketch a smooth curve through the points that I've asked you to the shifted points? It's like we've got an original function and a shifted function. Make sense? So draw the 2 curves and see how they work out. You can easily see what happens. Most of you have the graph. Some people making bigger graphs already, so give you enough time to do that. But if you do, it's pretty clear that you're going to get something like this. And something like this. Okay. Every point on this curve, if the curve is drawn perfectly, is going to be 1 unit to the right of this one, right? Because all these points are 1 unit to the right. So the whole curve, if you draw it in the same pattern, your 4 points are going to make exactly the same pattern here as they do here. Okay, now you can't draw it perfectly, but you understand that if it's drawn perfectly, that would be the case. So I can now say that everything over here is 1 unit to the right. And this curve has exactly the same shape as this one. Again, if it's drawn perfectly. So if I just slid this curve over here, it would fit right on top of this one. Now, the way I drew it doesn't quite exactly have the same shape. Because I can draw it perfectly. Okay, well, anyhow, this curve is shifted 1 unit to the right. Now, I'm saying this all again. This graph curve drawn perfectly through these 4 points that you shifted should have exactly the same shape as these because the series of 4 points has the same shape. Didn't get it quite exactly right, and neither did you because we're hand sketching these things, but it's fairly easy to understand that now every point then on this curve, if everything's drawn perfectly, is going to be 1 unit to the right of this curve, corresponding point on this curve. So if we just draw a bunch of arrows, 1 unit to the right from the points on this curve, we're going to get points on this curve. Then we recognize that these coordinates are part of the graph of the y equals x squared function, basic squared function. And if you think about that, if you've drawn that thing several times, you understand that. You should understand these basic functions well enough that that's obvious. Okay? You should know the coordinates of the function well enough that you recognize it when you see it. And you know the shapes of the functions. So as, for example, when we were talking about the domain and range of these composite functions, you know what the graph of the exponential function is, what that tells you about domains and ranges. This is very important. Okay. And I'll also say, I think I said it last time, there are two things that we do to our basic functions to build the functions that we use for almost everything. That's composites that we just talked about, and transformations that we're in the process of talking about. Okay. Well, anyhow, I asked, what's the formula for this graph? Well, I wouldn't expect you to know or be able to answer, although I should have given you more of a chance to show off if you did. But so if you knew and weren't able to establish yourself in the glory of answering that question correctly, you'll have other chances for glory in this course. Okay, mathematical glory. Okay, formula for this graph. I'm saying that the formula is y equals quantity x minus 1 squared. Now we're going to verify that. So if x equals 3, what do you get for y equals x minus 1 quantity squared? You want to show me with your fingers? Yeah, you get, if you subtract 1 from 3, get 3 minus 1, which is, and if you square, you get 4, right? Okay, so I'll write it out. Okay, so write it out in a complete statement. If x equals 3, y equals 3 minus 1 squared, which is 4. So the point is on the graph of y equals x minus 1 squared. 3, 4 is on the graph that we just constructed. So 3, 4 is on the graph of this function shifted 1 unit to the right. Okay, now let's make a table, just verify that at least all the x values that we got this function. The x values are 1, 3/2, 2, and 3. Let's evaluate x minus 1 squared for each of these values. For 1, we already got it. Three minus 1 squared is 4. 3/2, 2, 3. If you plug those into the x minus 1 squared function, what do you get? Okay, I did a really bonehead thing here. I've done 3 minus 1 squared over here, so I wrote 3 minus 1 here, but x wasn't 3, it was 1. That would have been 0. Okay. And then if you do 3/2, if x is 3/2, you're going to get well, that's going to come out 1/4 because 3/2 minus 1 is 1/2. Square that, you get 1/4. And I really apologize. Okay, does that make sense? Sorry if I confused you. It would have been much better if you done those calculations in the order I have. But we understand that these are the values you get. Okay, you can verify them easily. And if I now graph these points, I get 1, 0, which is here. 3/2, 1/4, which is here. 2, 1, well, there's your point. 3, 4, there's your point. Okay. So what we can say is y equals x squared is shifted 1 unit to the right. New graph has the equation of formula y equals x minus 1 squared. Okay, so shifting it 1 unit in the positive direction, we're going to subtract 1 from all the x values. For example, if you work it out, makes that very plausible. Bigger deal here is that this generalizes to any function. If the graph of y equals f of x is shifted 1 unit to the right, and I'm not going to say h units, I'm not even going to say to the right, because you could also shift the graph to the left, right? I'll say horizontally. Horizontally means to the right or left. Okay. So if h is 1, well, then it's kind of like what we saw. If h was -3, then we would want to use x plus 3. Okay, but the sign here is going to be opposite the sign of h. You're going to read about this. You're going to see the explanation. And the equation is going to be y equals f of x minus h. Now, if f of x is x squared, note that f of x minus h is x minus h squared. Replace x by x minus h, we get this, which is x minus 1 squared. So this is an example of this. A comment that if h happens to be negative, meaning if you shift left, then you're going to get a positive here when you do a negative with a negative. You'll see all this. That's the example of a horizontal shift. There are also vertical shifts and vertical stretches and even horizontal compressions. They're easier to understand. Okay, this is a hard one to understand, so that's what I wanted to show you. You'll see it, you'll see the rules. Think about why the rules apply. Because in the other cases, it's fairly easy to see. Horizontal compressions are a little tricky. But Vertical shifts and vertical stretches are pretty easy to say.